Yeah.
Well, because like it's a
The multiple choice.
Please, no multiple choice on the test. That's what's going to be the problem.
Yeah, but
Multiple
you're not
choice is scary. If I can explain it, I can see my errors.
like at the top of the magnet.
Not have
Top of the magnet is.
He knows that.
Yeah.
Oh, that's another problem.
Okay, so imagine this. Now we're gonna have moving things in magnetic fields.
No.
Oh, yes. Okay, so I have a conducting plate, okay?
I was young and stupid.
Means that the particles can move within it. And so I'm gonna drag this piece of metal through a magnetic field, okay? I'm gonna drag this thing in this direction in a magnetic field that's going into the page. So here's, if you're a proton within that conducting plate, what are you going to feel? Are you gonna feel a push towards the top or a push towards the bottom?
Push to the top.
Because if you take your hand, take your thumb and move it this way, because that's the direction that that particle is moving, right? You put your hand in this direction, the force is going to be going upward. So what you should see is that the top of the plate is becoming positively charged, right? Now, that means by contrast then, if you were an electron, what would you feel?
It doesn't run for it.
So if you use the left-hand rule, and it's going that way, okay? So if you pull it that way, you use the left-hand rule, and the magnetic field is going into the page, the electrons would get forced down to the
Bottom of the.
bottom of the page, right? Okay. So knowing that, Will Stanley, what's the direction of the electric field within that conducting plate? Is it pointing up or pointing down?
Down.
Why?
The positive test charge. It says so.
The positive test charge.
Yeah, it says
That's
so.
like, why does it go the right-hand rule?
Yeah.
I mean, he's right. Yeah.
So, what about the positive test charge, Will Stanley?
It goes down
Why?
because
Two reasons.
it's repelled by the positive side and then
Yeah.
attracted by the negative side.
So, if you put a positive test charge in here, why the positive test charge? So, that's funnier than it should be. So, it's gonna be, two things gonna happen. It's gonna be repulsed by the positive, and it's gonna go down towards the negative. Now, so, what's gonna happen is that you can create a force acting on a charged particle. So there's three criteria that have to happen. Number one, you have to have a charged particle, okay? Neutrons don't feel anything because they don't have a charge, which is why it's incredibly difficult for us to find neutrons, because there's two reasons why it's almost impossible to find neutrons. Number one, they don't respond to electric or magnetic fields. Number two, they tend to be bound up in the nucleus and attached to other protons. So it isn't like you're gonna see like a random neutron walking down the street going, wow, hey, there's Nettie the neutron, okay? No, it's not gonna happen, okay? So it's incredibly difficult to find them because they don't interact with these things. Now, the other thing that has to happen is that you have to have a velocity. Because again, Mother Nature is going, hey, if this thing isn't moving, great. I don't have to worry about it. I'm not going to create, nothing's gonna move, I'm just gonna let everything be.
Hello.
And then obviously, you have to have it moving through a magnetic field. So without a magnetic field, nothing's going to happen. So the sine theta part, unless you're explicitly told differently, what do you think the angle is gonna be?
90 degrees.
90 degrees, and you
Somewhat.
don't have to worry about it because the sine of 90 is gonna be 1. Okay, now, we're gonna do a little bit of creativity here, okay? Just a little bit, not much. So, if this thing is, what we're gonna do is we're gonna set an electric field equal to a magnetic field, okay? So, as this thing is pulling through, the electric field that you can generate could balance out the magnetic field. So all I'm gonna show you is where this equation comes from, okay? Don't flip out, this, all I'm just showing you is where it comes from. Now, what's the easiest way to calculate the strength of an electric field? Fact, right? Oh, that's gonna be EQ, right? That's all you got. F equals EQ. Then this is gonna be QVB, right? Now, because this is this force from the magnetic field. So that's just gonna be QVB. You've seen this before. So what's gonna happen to my value of charge? That's gonna cancel out. Okay, we don't have to worry about that. Now, voltage, if you remember, can equal a whole bunch of things, but what's a simple way to express voltage? Voltage equals, well, no, this is like electric fields and things like that. Huh? Somebody said it.
ED.
Yeah, voltage equals E, right? So if you solve this for E, you get voltage over D. So I'm gonna come in here and put, now, here's where this gets complicated. Don't confuse the V for voltage with the V for velocity, okay? It's tricky, but stay with me here. So this is going to be over L. Now, I'm gonna put L because that's gonna be the length of the wire or whatever that's actually in the magnetic field. So it's still gonna have a unit of meters, but it's gonna be the portion of the length that's actually in the magnetic field. So I'm just gonna do a little bit of hocus pocus. So then you got, this is still velocity times your magnetic field. Now, if I solve this for voltage, I get believe. So, this is just kind of what I showed you back there, okay? So, I created a voltage in that solenoid. So, when the magnet that I was moving was at rest, I didn't have a voltage, okay? There wasn't anything there. So, the magnetic field, whatever that external magnetic field, that might be like the Earth's magnetic field. This has to be an external magnetic field. And then you're gonna have some length. Now, if you're a pilot, you need to be aware of this equation. So, give me a second while I draw an airplane. I have to draw it like three-dimensionally.
Just be thankful we're not using air resistance.
That's such a thing for this generation to say.
I'd like to see you go.
Is he have creativity? You just play graphic designer.
No, X one.
We'll have ChatGPT do it for us.
Honestly?
Okay, airplane is
What about the word?
Sometimes your drawings, like, I can't tell what they are unless you dictate it, but this is definitely that's a plane. That's a plane.
It's like a jet to me.
Good.
This is like the most original
It's
thing.
a rocket. It's obviously a rocket.
I do believe that plane can fly.
That is the dream.
Maybe my one.
It's either got aliens.
50,000 a year.
I have
Probably because it's like a plane. If there's like plastic glider.
Yeah.
It's a glider. Yeah. Straight glider.
Who's this one?
Well, you know,
because it was such,
Not
its design was so good.
Not that word. Not that word.
That was all like, you get, it's like, it's not landing, you have to go by the hook.
I can't describe it.
this American plane that was so goddamn loud.
You can describe it.
It was a little
Yeah.
Thunder Streets, bro.
The concourse.
Thunder Streets
Okay.
was where
So,
it's about 900 something boom.
if you're a pilot, you need to worry about this idea, because what happens is you can create static electricity on the plane. So you have a plane flying at 260 meters per second, about 2/3 the speed of sound. And it's flying through the Earth's magnetic field. And the distance across the wings is 65 meters. That was pretty decent. That's a pretty big plane. Okay? About 2/3 the length of the football field. And what I want to try and calculate is how much voltage is going to build up across those wings. Okay? So the calculation itself is pretty simple. Oh, okay. So if you look, and here's where your book kind of does this a little bit, or the equation sheet does it a little bit weird. So your equation sheet has it as that fancy E, and then BLV. So that fancy E is like electromotive force. So electromotive force and voltage mean the same thing. So if you write that as delta V equals believe, that means the exact same thing that's on your equation sheet, but they have it in terms of the electromotive force. It's the exact same thing. So don't flip out and go, oh my God, the equation isn't on the equation sheet. It is, it's just giving us the electromotive force. So then it's just a pretty straightforward calculation. You got 5.0 times 10 to the negative fifth times the length of 65 meters, and you're traveling at 260 meters per second, and you get, crunch all the numbers, you get 0.85 volts. Okay? Now, that isn't a huge amount, but it can lead to a buildup of static electricity, which around a plane, when you're trying to fuel it, is a legitimate concern. Because you get the wrong spark at the wrong place at the wrong time, fueling your plane, that's kind of important. So sometimes what they'll do is they'll hook up like a grounding rod to the plane, because they know when it's flying and it's going through obviously there's a magnetic field, then that has the potential to build up charge. So if that's a concern, then they'll basically ground it. So it's just like you, if you've ever shuffled your feet on carpet in the wintertime and you're wearing socks, what do?
We're believing.
Yeah, you're building up a voltage, right? And so when you touch a knob or someone else, okay, your annoying little brother, you shock them because of the fact that you have, and what you're doing is just you're discharging that buildup of electrons. That's the same thing that's happening here. Okay, now, here's the part that's going to require the most thought.
No.
I'm going to tell you straight up, Connor S., okay? I'm going to tell you straight
Why are
up.
you talking to me?
Just because you're the one going like, I can't get it. those others.
Whoa, I've been killing that kid.
Not at the beginning of class.
It's because you're talking nonsense.
You might want to listen.
He's gonna shoot.
It's a rail game.
It's a railgun. I understand these. I mean,
No, this is not a real gun. Well, kind of.
It's a real.
Takes you down 3D. The college application, we make a real gun.
Did that you
It
guys?
looks like a railgun to me.
It's saying instead of the
Okay,
current and
so this is very much a multi-step problem, okay? So this is where you have to kind of go back to what we were talking about before. So kind of imagine this, you have like a U-shaped rail, and you have a wire across it like this, okay? And you have a magnetic field, an external magnetic field going into the page. So this is that wire. You have a piece that can move across it, kind of like a railgun. And then you have an external magnetic field that's going into the page. Got the visual. And so what I'm going to do is I'm going to pull this thing in this direction. So you can think of this as being like a curtain, okay? Like a stage. So when you pull this in this direction, it's like you're pulling back the curtain. And when you pull back that curtain, are you seeing more X's or are you seeing more O's?
Or X's.
Yeah, you're pulling back the curtain, so you've got all these X's. So imagine that you're pulling back the curtain. This is why I said this takes like 4 steps to get there. So the first step is that you have to realize if you pull it in this direction, it's like a curtain, and you're going, ho, there are the X stars. And you're seeing more and more X stars. But Mother Nature goes, seeing a lot of X's. Not digging it. So what's Mother Nature going to do to balance you seeing more X's?
Use the current to make more of it.
Oh, Mother Nature's going to use the current to make more O's. Okay? So in this region, imagine that you're pulling this block and you're seeing more and more X's. So Mother Nature's going to go, play your game. I'm going to make more O's. So what is going to be the direction in this wire to make more O's?
Has to be down.
I've heard up, I've heard down.
It's up.
No, if it's on the left, yeah, it's one.
So it's on this wire right here. In this region, I want to make O's.
Yeah.
So the current's going to go up, right?
The wire's like this.
Current's going up. That way, your right hand curls out this way. So the current is going to be going up. So that's the direction of the current, okay? So that's the first time we're going to use the right hand rule, okay? It's the first time we're going to use the right hand rule. Now that we have a current, and again, if you don't move that rod, you're not going to have a current. Why?
because only a
Because what's not changing? The field. If you don't move the curtain, Mother Nature's just going to sit there and go, just going to chill out. Nothing's going to happen. But if Mother Nature sees that curtain moves, she's going, oh, I'm seeing more X's. I got to make dots. I got to make current to oppose that. But if the curtain isn't moving, nothing's going to happen. Now, we have this. So Thatch, with feeling, said the current's going up. So now we're going to use the right-hand rule again. Okay? Now we're going to use the right-hand rule again. So the current's going this way, because now we have an induced current. The current's going this way. The external magnetic field is going into the page. That's going like this. So what is the force the bar is going to feel?
To the left.
Oh, in the opposite direction. So the force that it's going to feel is in the opposite direction, which is going to make it do what? So if you're pulling it this way, that's going to create an opposing force. Right? Now, then you could look at this and go, okay, well, the force that you would have to provide is given by belief. Okay, so your magnetic field, the length of the wire, and the velocity. But again, if the wire isn't moving, what's going to happen?
Nothing.
Nothing. You don't have to supply a force. Now, let's talk about this. Remember when y'all did, if you think back, go old school. Back when life was simple and we were just doing forces, okay? And it was like October.
I miss those days.
Oh, back in the day, I think it was in May. Oh, back in the day. And y'all did the lab where you had the strong magnet and you pushed it between the plates?
Yeah,
Yeah,
slow
that's-
down.
Oh, it always slowed down. It always slowed down. Because what it did is that created a current that opposed the change in the magnetic field. And that force is in the opposite direction, which is why it always slowed it down. Now, an interesting thing happens. What if I push the bar in that direction? Okay? Now let's just look. Your Mother Nature. The curtain's going to be coming across like this. What are you going to be seeing less of? X's. So you're seeing less X's. So what's Mother Nature going to do?
You gotta make more X's.
Oh, Mother Nature's going to make more X's. So what's going to be the direction of the current if Mother Nature is making more X's?
It's gotta be down.
Oh, then it's got to be down. So now the current's going this way. Oh, an interesting thing happens on the way to the curtain. The current, not the curtain, the current is going this way. What's the direction of the magnetic field?
Into the page.
Into the page. Ah, what's the direction of the force?
Right.
Ah, now the force is to the right. Still in the opposite direction that you are
Pulling.
pulling. Still going to slow it down. Okay? See the pattern. Okay. All right. Now, your Mother Nature, sitting out in the audience, and you see no stars, and you see no dots, and the curtain opens. What are you going to do as Mother Nature? Nope, nothing. You are going to do absolutely nothing. Why?
There's no magnetic field.
Yeah, there's nothing changing. There is no changing magnetic field. So if I pull that wire and there's no magnetic field, guess what? Mother Nature's going to go, well, that's exciting. And she's just going to chill out, okay? So that's the whole point. If there's no magnetic field, nothing's going to happen. Now, you're Mother Nature. You're sitting out in the audience. You see the curtain. But the curtain isn't moving, but you see stars. Or X's. Let's go with X's. You're Mother Nature. The curtains are there. You're seeing X's. But the curtains aren't moving. What are you going to do?
Nothing.
Absolutely nothing. Why? Because nothing is changing. Okay? This is the one time you can use the C word. Okay? Changing. Okay? Or it's different. Right? So, here's the story. Your Mother Nature, and you have to understand this concept. Your Mother Nature, you see the curtains closing and you're decreasing the number of X's that you see. What are you going to do?
Increase the current, increase the X.
Yeah, you're gonna make more X's. So if you decrease X's, you make X's. But if you open up the curtains and you see more O's, what are you gonna do?
Make more X.
Then you're gonna make X's. So if you see more of one, you make the opposite. If you see less of one, you make the same. Okay? Got the idea? One of the most important things that you have to understand. And again, if nothing changes, what's going to be the current? Nothing. Okay, now we need to do a little bit of algebraic voodoo.
No.
Oh, it's okay.
But which way does the motion go? Removing it to the right. Yeah.
I'm saying this physics lecture.
So.
After lunch,
How would you?
The motion is,
maybe lunch was like today.
the force is opposite.
No change.
I actually enjoyed our phone discussion today. I actually participated.
Or something.
But what's the most, what's the force?
Which gives me like a
It's
minute.
gonna, well, because you're pushing it in, the force is gonna go.
But that's not what the right hand here says. No, because the wire current's moving up.
I think so.
Still,
I think she's protective of
the
him.
current, we switch.
Yeah,
the
that's
current.
yeah.
No, he doesn't like
Because
that.
the
No, she
field
doesn't
that
like
has
it.
to be made,
Yeah, I remember
I don't think she
talking
really
about
likes
dictates the.
She doesn't like the race.
Oh.
I guarantee you she likes everyone.
Okay, for sure, everything.
No.
Right there, you see it?
Yeah.
No, that's
I don't know
called.
if she likes me, but she respects my opinion.
It's not. I think that's what she did. She talked about like World War II and how that was happening.
Oh,
Yeah.
so that was just for being dumb and I didn't like want to correct her.
What did she say? What's your argument?
Both.
Yeah, but.
She
Both
said,
are
well, he did
true.
know it was
Absolutely.
between two wars. And I was like, no, he didn't. When we were talking about World War I,
Wow, I suck at this.
I was like, technically he didn't know he was between two worlds, and she said something like,
Yeah, we're writing a lot of things on the board.
I know. It'll all come together.
That makes sense though. I don't know about this one, but it all makes
when you
sense.
like started shooting me and stuff like that.
Oh, yeah, that, because he was in India
And
It's like the 1920s.
my thing was the Second World War kind of happened yet, he doesn't know he's in between it. And she like tried to say something else, and I was like,
He wrote it in 1920s.
It's going to be easier if I get it all written out, and then.
Is this the reason why you take so many English classes outside of school? See,
Time to do this when I get
hey, just remember, if you do it sideways, it makes you more popular. But if you go down the street, it gets the job done.
Yeah,
You're not email enough to know this.
he wouldn't have had any.
I'm not, what?
You're not email enough to know
Yeah,
that.
I'm not emailing now.
Okay.
I need to.
So if you do a little bit of hocus pocus, this is why I said this is easier if I just get it all written out at once. So anytime you have like the force from the pole and the force from the magnet going in opposite directions, you can set them equal to each other. Okay? So all I did was I said, okay, the force from the magnet is going to equal ILB. Okay? Bill, however you want to put it. So, to back up a little bit, if you ver it up, okay, old school ver, right? This is why you study circuits before you study magnetic fields. And if you set that ver, and then you solve for the I, you get BLV over your resistance. So all I did was just some simple algebra. I substituted, instead of voltage, I put IR. And then I solved for I by setting BLV over R equal to the current. Okay? That's all I did. Then I said, okay, well, the force from the magnet is ILB. That's all I got. So then I took this, BLV over R, leave over R, and substituted that in for that current. Okay? That's all I did. It was a simple substitution. So now I've got believe over R times LB. So then if you combine these terms, you've got velocity times L squared B squared over R equals the force from the magnet. Now, the reason that you do this is because of the fact that these values here are relatively simple to measure. Oh, what's the velocity? And obviously this only works if your velocity is constant. Oh, it traveled a certain distance in a certain amount of time. Your L, okay, what's the length of the wire that's moving through the magnetic field? Oh, the magnetic strength. Oh, we can take a sensor and measure the magnetic field strength. Oh, if we know the length of the wire and the type of wire, or we just measure the resistance, that's an easy thing. Now, an interesting thing happens. If you increase the resistance of the material, actually what happens to the force that it's going to take? Takes less. So that's a little bit counterintuitive, because you would think, oh, right, more resistance. But here's the story. But here's the bigger picture. If you increase the resistance, what happens to the current?
Decreases.
The current becomes less. So then if you go back up to ILB, oh, if you have more resistance, you have less current. That decreases the strength from the magnetic field. Okay, one last equation. And that's power. Okay? So what's the simplest way, old school, simplest way to calculate power? No, that was a beginnings.
Over time.
Simpler. What? Somebody said it.
Work over time.
Work over time. Okay? Work divided by time, right? Old school. True? Now, what's the simplest way to calculate work? Force times distance, right? Over time. But distance divided by time is velocity. Okay. So you can write power as force times velocity. But we just said that the force is V L squared B squared over R. So then if you substitute all of that into here, then it just becomes V squared B squared L squared over
Just do VLB.
equals your power. Okay?
That's velocity.
Yeah.
Leave it a square.
Not voltage, it's velocity.
Squared over R.
Now, let's go even farther back. What's the simplest way to calculate power? Simplest way. No. In terms of an electric circuit.
That's not that far.
Pivot, right? True? What's another way that you can write power?
I squared R. I squared.
Which does make sense.
I squared
Oh.
R?
E squared over R.
Or you can put it as V squared over R. Well, what, Gavshan?
And then V equals big. It's the same thing.
Oh, it's the same thing. So if you take for voltage, if you put in how you can calculate voltage, you end up with the exact same thing. Ah, okay.
Brain hurts. I'm feeling dramatic today.
It's not an incision. No, dude. I'm jumping up and talking about me.
Right, so basically, here's all that time
Yes, I was right. It is 25.
perfect. My favorite.
Not that I care that much about it.
Anything but that kind of stuff. I'm gonna bring many
I was still debating.
Do you think I can?
Yeah, no, you can do it. Yeah, you can do
I was
it.
still debating it.
I'm bringing. Well,
What is it?
Why would I do
Annoying.
what can I do?
Oh no, classic.
Such big.
Going into oh my god.
Yeah, that was due.
Yeah, I was sick at it.
No, I wasn't here Friday.
You can find something in your
The
house.
only part that matters is that I thought about it.
When you get to, that's it. I'm done.
How hard are these problems?
That's a
How could you make us do all this work?
Guys, be thankful.
Okay.
Thank you.
Well, no, don't thank me yet.
Yeah, it's about
Back to
When you get to question 3, now 3 has like A through F. But there's no calculation. So,
That's worse.
okay. All of your answers on A through F, you only have 3 options. It's either clockwise, counterclockwise, or 0.
Oh, okay.
So what question 3 is relating to is imagine changing your Mother Nature. And you're sitting out in the audience and you're seeing the stage, okay? So remember, if you see more X's, you are going to make more O's. If you see fewer X's, you are going to make more X's. If you see nothing changing,
Nothing happens.
nothing happens. Okay? So let me give you a hint. On number question 3, you should have 3 zeros. Okay? So when you get down on question number 3, you should have 3 of them that have no current. Okay? Just telling you. When you get to question or problem 4, because if that's wrong, 4B is going to be wrong. So your answer to 4A should be a little bit above 1 amp. Because if that's wrong, 4B is going to be wrong. On number 7, you have to, the question's going to be about a truck moving through the magnetic field of the earth and which direction is the electric field. So you have to visualize the side of the truck, which direction the truck is moving, and which direction the magnetic field is moving in terms of the truck, okay? So on number 7, the most difficult part is getting the visual in terms of the direction that the truck is moving and the direction of the magnetic field relative to the earth, okay? So just keep that in mind. All right, I'm done, you're on your own.